So, again we start a new lecture. We will just go through the last lecture and its contents, and then we start the new topic. So, basically this module is about the nonlinear dielectrics, and we started our discussion with a general discussion on dielectric materials, nonlinear dielectric materials, and how they can be distinguished on the basis of crystallography. So, we found out that the classes that we are discussing relate to what is called as non-centrosymmetric materials, and even among non-centrosymmetric materials you can have variety of constraints. So, starting from that, we started with ferroelectric materials, and ferroelectric materials are actually most important of these, because they possess the properties which are unique, and other nonlinear dielectrics basically are subset, are any ferroelectric becomes, for instance, piezoelectric and pyroelectric. So, that is why we started our discussion with ferroelectric, and characteristic of ferroelectric materials was that they undergo a phase transition when cooled or heated, and this phase transition is typically when you cool it, for instance, from a high symmetry phase to a low symmetry phase, and this is associated with occurrence of ferroelectricity in the low temperature phase. And this you can see in terms of dielectric constant or susceptibility, and depending upon how the polarization, dielectric constant, susceptibility change, the phase transition can be of first order and second order. And then we stumbled across the ferroelectric hysteresis loop, and in that we found out what happens when we pole a ferroelectric, which means that when you apply electric field to a ferroelectric materials, what happens to its polarization. So, of course, you come across a hysteresis loop. What is the reason for this hysteresis loop, and two non-zero states at zero field, and this was explained on the basis of domains. Now, domain was basically defined as a region of uniform polarization, but you can't have a monodomain state, because that is energetically unfavorable state, because then the depolarizing field becomes extremely high. So, based on these constraints of depolarizing field and electrostatic energy, the domains, monodomain state divides itself into multiple domain states, and the type of domains that you will have, of course, is type of domain walls that you will have is of course determined by the crystallography, but in general you have variety of these domain walls which give rise to these domains. Now, what happens at zero field essentially in a ferroelectric is that you still have some domains oriented in the direction of applied field, and one of the important things in ferroelectrics is that when you switch the ferroelectric material, or when you pole the ferroelectric material from highest electric field to lowest electric field, or vice versa, highest and lowest in terms of polarity. So, minus E to plus E, for instance, then since the domain have to switch back and forth from one orientation to another orientation, in these materials this happens by nucleation and growth. So, whenever you change the field polarity, it is always the new domains which form by the process of nucleation, and then they grow into the crystal at the expense of old domains. So, for instance, if you start from a domain state, let us say you start from a domain state like this, and so which means at this point the electric field was also like this. So, when you now reverse the electric field, you go to this direction, then you have these domains which are nucleating, and they are in the opposite direction, and these domains grow as you reach the saturation field, or field required for saturating all these domains, and that is what results in this classic hysteresis loop. So, you have a hysteresis loop, and these are the non-zero states, minus PR and plus PR, and what you have is minus EC and plus EC. And then we looked at some other then we looked at an analytical treatment for domain wall width, and we found out that this domain wall width is related to the polarization of the crystal as well as the surface energy of the domain wall itself. And so, naturally, larger the domain wall energy is, larger the domains will be, because you would then require to spend more energy in creating many more domains. So, as a result, the energy requirement forces the domains to achieve a larger size, but at the same time, if the polarization is larger, then again domain becomes smaller, because larger polarization means the larger depolarizing field, and then more driving force towards forming domains. So, it is the competition between these two energies which forces the domains to achieve a equilibrium configuration of a particular size. And then of course, we looked at some other intricacies related to ferroelectric materials, followed by the applications. Most touted application for ferroelectric material of course is the ferroelectric memory, and due to inherent advantages as we discussed last time, but it can also be used as a piezoelectric and pyroelectric, and that is what is they have been used for centuries. Now, the topic of this lecture is essentially piezoelectric ceramics. Now, piezoelectricity is basically an interesting effect, which is essentially, if you look at two terms, piezo and then electric. Piezo relates to stress or force, piezo, and then electric means you have of course electric. So, it is coupling of stress and electric field, or coupling of mechanical parameters with respect to electrical parameters. And this is what makes these materials extremely interesting, because when you apply stress to them, you have electrical response, or vice versa, when you apply electrical stimuli, you have a mechanical response, and this makes them extremely useful for variety of applications, and as we will see later on. Now, this effect piezoelectricity was discovered in 1888, I am sorry. By Curie in 1988, and this was essentially called as, at that time, or this was later called on as, direct piezoelectric effect. And basically it was observed as some materials having capability to create an electrical potential in response to the application of mechanical stress. So, what was observed was that a stress was applied, and this gave rise to let us say a polarization or a field or whatever, some electrical response. So, this was observed by Curie in 1988, and for a variety of reasons this application of stress leads to the changes in the electrical parameters. So, one of the requirement for this was that and another thing was before we go into the requirements, another the converse piezoelectric effect, and soon after this discovery of piezoelectric effect in 1888 by Curie, then you had this discovery of indirect piezoelectric effect. And this happened in almost a year later. And so, roughly around 1880s, you had these studies by Curie, which led to direct piezoelectric effect, followed by demonstration of indirect piezoelectric effect soon after. And then this was later studied in a variety of materials. For instance, quartz was one of the early materials which was studied, and then you had topaz and tourmaline, sugar, or rather cane sugar, and then you had this Rochelle salt. So, all of these materials were studied in the beginning after the discovery of piezoelectric effect in 1880s by Curie and other scientists. Now, this piezoelectricity, the moment people knew that this is an effect which couples the electric and mechanical parameters, this soon started realizing variety of applications, and from the application point of view, the major impetus to the piezoelectric devices came from World War, the requirement of devices in the World War. So, there was a major impetus given in World War I. For instance, the sonar devices which were developed from piezoelectric effect were first developed during First World War, and then later on, of course, a lot of these applications came in Second World War as well. New class of piezoelectric materials were made as a result of the requirement and ongoing research and development in this area, and that is how piezoelectricity got a lot of prominence during the World War. So, what we will do is that we will first develop a general framework for piezoelectric materials. What is this effect, what sort of materials show this effect, and then later on what are the types of different effects, and look at the mathematical expressions on how to express this piezoelectric effect mathematically. So, essentially, if you look at the first topic, which is the mechanism, and mechanism is essentially when you apply stress. So, you take a material, and when you apply stress to it, the stress essentially produces an electric signal, and this electric signal is in terms of some sort of charges on the surface of the hang on, let me just get this picture right. So, some sort of charges on the surface of the piezoelectric material. So, this is basically a polarization, but it is not only surface charge, mind you, this is happening inside the piezoelectric. So, what you have inside the piezoelectric is the displacement of dipoles or the development of polar vectors of dipoles inside the piezoelectric. So, when you apply stress, so application of stress to a piezoelectric material leads to changes in the dipole orientations, and hence changes in the polarization. So, you should not confuse piezoelectricity with only a surface effect. The effect of applied stress, for instance, is felt inside the material, and as a result of changes occurring inside the material in terms of dipolar arrangement, you have the surface charge which is being developed. So, and normally the field that you may require to apply to these materials can also be very small. It depends upon what is the coupling coefficient of variety of materials. But for instance, if you take quartz, you do not require a very large field. So, if you take a quartz piece of 1 centimeter cube, so 1 centimeter cube is essentially 1 centimeter by 1 centimeter by 1 centimeter. That is the simplest way to think of it. And then when you apply a force, for example, of 2 kilonewton. Now, this 2 kilonewton is very small force. I mean, if you just divide it by 2 into 10 to the power 3 Newton divided by 9.8, which is approximately 200 kg. So, if you apply just this a smaller force, 200 kg equivalent of force, then what you get is a voltage, it can exceed 10,000 volt. So, just by applying a force of 2 kilonewton, the voltages of the order of 10 kilovolt can be generated on a small crystal as small as 1 centimeter cube. So, this piezoelectric effect is extremely strong. So, it is not merely a surface effect, it is a bulk effect. It comes from the interaction when you apply stress, it comes from the interaction of the dipoles with respect to each other and the tendency of them to align along a particular direction during the application of stress. And the other effect, which is called as converse piezoelectric effect, where you apply electric field and this causes the change in the mechanical dimensions or causes mechanical deformation in the crystal, which we will see in a while. So, how do you express this effect? First of all, what sort of materials do show this effect? So, materials, firstly, the materials need to be non-centrosymmetric. And this we have already discussed in the beginning of module 5. Non-centrosymmetric materials are the materials which do not have a center of symmetry. Okay. So, any material which has a center of symmetry will not be piezoelectric. So, this is one of the this is the most important requirement for a piezoelectric material. It has to be non-centrosymmetric. On top of that, anything happens, that is further additional constraint, but it has to be non-centrosymmetric in order to exhibit any kind of piezoelectric effect. And what basically it means is that, and then you of course you can have polar and non-polar materials as well within this class. Now, whether it is polar or non-polar will determine whether it is pyroelectric or ferroelectric, but it does not concern with material being piezoelectric. As long as it is non-centrosymmetric, it is piezoelectric. And so, the crystal classes which show this kind of effect are, so you have 1, 2, M, MM2, and then 4, 4mm, and then 3, 3m, 6, and then 6mm. These are all polar groups, polar and non-centrosymmetric, and then you have 1, 2, M, 2 to 2, mm 2, 4, 4 bar, 4 to 2, 4 mm, bar 4 to m, and then 3, 3 2, 3 m, 6, 6 bar, 6 double 2, 6 mm, bar 6 2 m, 2 3, and then bar 4 3 m. So, you can count the polar groups which are 1 2 3 4 5 6 7 8 9 10. 10 are polar, all these 10 are included in these classes which are written below. So, these are all non-centrosymmetric. So, these are all piezoelectric in nature. Okay. So, polar materials are the materials which have a spontaneous polarization. So, which means they have a unique polar axis, and the materials which show this effect are both natural and artificially made. So, so for instance, you have berlinite. This berlinite is basically aluminum phosphate. So, this is a very rarely found phosphate mineral, whose structure is pretty much similar to quartz, and this is again a piezoelectric material. As I told earlier, cane sugar, and then you have quartz, and then you have Rochelle salt, and then you have topaz, and then you have tourmaline. All these are naturally found materials. So, nature provides us with materials which are inherently piezoelectric in nature, and of course, the most important of them being quartz. I mean, quartz has been used in a variety of applications, including the watches that we wear. And then of course, the materials which are synthetic materials. Synthetic materials you can have starting from barium titanate, a very famous, it is a ferroelectric actually, but since ferroelectric material is by default piezoelectric, this has been used for piezoelectric. So, this was the first ever man-made piezoelectric. So, barium titanate, then of course, you have lead titanate, and then you have lead zirconate titanate, solid solution of lead zirconate and lead titanate, and then you have potassium niobate, and then you have sodium tungstate, Na2WO3, and then of course you have lithium tantalate, lithium niobate, and so on and so forth. This list is very long. Of course, you have Bi complex oxides like Bi4 Ti3O12, Sr Bi2 Ta2O9. So all of these are man-made or synthetic piezoelectric material. You can have many other naturally occurring materials, such as bone is also a piezoelectric. It has some piezoelectric effect, and also you can have wood represents a piezoelectric material. You can have silk, which can have some piezoelectric effect, but majority of the piezoelectric materials that we discussed, which are naturally occurring, are these. And in the next slide, basically these are the synthetic materials of piezoelectric type. Now, what we will do is that we will look at now the mathematical expressions which are used to express the piezoelectric behavior. Before we do that, just a small remark on the previous slide. If you look at it here, most of the materials which have piezoelectric effect tend to contain lead, and this lead nowadays has been termed by variety of countries as a poisonous material. So, one needs to find alternative to the lead free material, to the lead containing materials, which means we need to find lead free materials, and there are some lead free materials, and those are, so Pb free materials, Pb free materials can be your BiFeO3, although it has of course issues with respect to being used as a piezoelectric. And then NaNbO3, sodium niobate, and then sodium potassium niobates, etc., etc. So many of these materials which do not contain lead are in contention nowadays, simply because of the fact that lead is not a very healthy material, healthy element. Now, what we will do is that we will look at the first we will look at the direct piezoelectric effect. A little bit more quantitatively, so that we are able to understand it better. So direct piezoelectric effect occurs when applied stress to a material gives rise to change in the surface charge density. Or change in the polarization, and which can be detected as either electric field or potential across the sample. So, essentially mathematically what it means is that P, the polarization, is equal to d dot sigma. Now, these have to be explained more correctly in the vector notation, which I will show you in a while. So, this direct effect in the most easiest form is expressed by this equation. P is equal to d dot delta, where P is of course the polarization, d is sigma is the stress, and d naturally is called as a piezoelectric coefficient, and this is actually a third rank tensor. So, now what basically it means is that pictorially you have a material and when you apply when you apply stress to this material, let us say like this sigma, then you have polarization appearing like this, and when you reverse the magnitude of stress, if you make the stress like this, then polarization also reverses its direction. So, this is what is direct piezoelectric effect. And essentially here the stimuli, so this is sigma. So, stimuli is stress and changes in polarization or directly charged density, whatever you may want to call it. So, this is what is direct piezoelectric in the simplest form. Now, the second effect is converse or indirect piezoelectric effect. Now, in the indirect piezoelectric effect, what happens is when you apply electric field, you have deformation in the crystal. So, what basically it has is it's represented by epsilon is equal to E multiplied by D. So, this epsilon is the strain, E is the electric field, and D is the converse piezoelectric coefficient. Okay. And so, here this electric field acts as a stimuli and this strain is the response. So, you can understand the converseness with respect to the previous effect. So, what it basically means is that you take this crystal. So, when you apply electric field, for instance, in this direction, then it sort of expands. So, this is the new direction. So, electric field was in this direction, and if you change the electric field to other direction. So, if you reverse the direction of electric field, so if I make now electric field in this direction, this will contract. So, this is what is the converse piezoelectric effect. So, these are the two effects which are of importance to from the point of view of fundamental understanding. And what now we will do is that we will have a look at the now these are all, if you look at here in the equations here, the stress is a tensor, as a result D is a tensor, which is the piezoelectric coefficient. Again here electric field is a vector, strain is a vector, as a result this is also a vector. So, it can also be expressed in the form of vectorial notation. So, for instance, the strain, let us say epsilon, or let us say here we define first the terms. So, if I say stress is sigma, strain is, just not to confuse with the electric constant, let us say strain is E, and compliance is small s, electric field is E, and what else, and then we have D as a piezoelectric coefficient. So, we can write in the form of coupled equations. So, we can write this as, so strain can be related to and then of course, you can relate D, I forgot to mention D here, D is the dielectric displacement. and this you remember from module 4. So, D can be related as epsilon sigma into E. So, here this is the first one is the D is the matrix. So, here so this D basically is the matrix for. So, these are called as coupled equations, okay, because they couple the electric field and stress effects. So, D here makes a matrix for direct piezoelectric effect, which is this, and dt makes the matrix for basically converse piezoelectric or piezoelectric effect. And this t term, small t term, is basically the transposition of matrix. So, if D was a direct matrix for direct piezoelectric effect, the transpose of it would be the converse piezoelectric effect. So, you can basically express the piezoelectric effect, since the terms related here are vectors or tensors. As a result, you can express them in the form of matrix. And basically the subscript here. So, you have these subscripts here, a capital E, sigma, and these subscripts essentially mean a constant or a zero field, and similarly zero electric field, and subscript of sigma will mean constant or zero stress field. So, basically this would be your converse piezoelectric effect, and this is your direct piezoelectric effect. All right. Now, you can do so based on this you have variety of piezoelectric coefficients as well, and in total there are 4 piezoelectric coefficients because of this vector notation. So, you have 4 piezoelectric coefficients, and these coefficients are, so first one is d I j, and this d I j is del of d I to del of sigma j at constant field, and this is also equal to del of E j to del of E I at constant stress. Similarly, you can also have another one as E I j. This could be del of d I to del of epsilon j, or epsilon instead of epsilon I should write E j at constant field to, and this is also equal to del of sigma j to del of E I at constant strain, which is E. And then you have G I j, which is minus of del E I to del of sigma j at constant d, and this is equal to del of E j to del of d I at constant stress. And then last one H I j is equal to minus of del E I to del E j at constant d, and this is equal to minus of del sigma j to del d I at constant strain. So, these the first set of 4 terms, which is here, this is your, these are your direct coefficients related to direct effect, and these ones, as you can see here, are related to indirect indirect or converse effect. So, and you can see details of these mathematics of piezoelectric materials or piezoelectric terminology in variety of books. For example, the books by, so there are books by Kenji Uchino, another book by Helen Megao. So, these are two authors who have written really nice books on piezoelectricity. So, if you want to go into details of this, you can go to these books and refer for better understanding. Okay. So, what now we will do is that we will now look at some of the aspects related to piezoelectric materials. Now, piezoelectric materials, likewise ferroelectric materials, they also have domains, and these domains, so domain of course is a region of uniform polarization. What happens in a piezoelectric material is you need to pole a piezoelectric material in order to get anything out of it. So, what happens is that in the beginning of the poling, before you pole it, all the domains are randomly distributed. So, what happens is that if you draw a picture of, if I draw a schematic diagram of such an effect. So, the topic is basically poling of piezoelectrics. So, if you take typically, so this is, let us say, the grain size so this is a typical polycrystalline material, a ceramic. Okay. So, this is polycrystalline ceramic. Okay. Now, before you have poled for a piezoelectric material, before poling, what happens is that in this material, let us say I divide this in variety of domains. So, these are our grains, okay, and within these grains you have domains. So, let us say our domains are like this. Okay. Now, let us say we have a random distribution of, before poling, what happens is that we have a random distribution So, this is the picture which emerges just before the poling, and basically what it means is that you have a random distribution of domains. So, random distribution of domains before poling. So, if you have random distribution of domains, so even though material is polar, it has individual domain having finite polarization. The net polarization PR net is equal to 0. So, what you need to do that in order to use this as a useful ferroelectric material, what you need to do is that you need to apply electric field to this material. So, when you apply electric field to this material, let us say in this direction, then what happens is that this material changes its domain structure. So, as a result, what you have is essentially you have a change in the dipole alignment. So, now the picture can be slightly different. So, if I draw now the electric field to this material, they are not going to look exactly similar because these are all handmade drawings. Okay. So, these are grains. Within these, of course, you have grain boundaries. So, essentially if the electric field was like this, you have more domains in the direction of applied field. So, essentially you have bigger domains which are oriented in the direction of applied field. So, essentially you have here so essentially you have a larger application of field leads to domains aligned along the field. So, as a result what happens is that when you remove the field, so of course, this E, as the E increases, the PR also increases, but when you remove the field, this all these domains do not come back to their original situation. So, as a result what you have is when E is equal to 0 after poling, PR is not equal to 0, and this is what you want. You want some polarization to be present inside the material. So, you need to. So, the important requirement for a ferroelectric material is that you need to for a piezoelectric material is that you need to pole it before you use it as a piezoelectric material. So, now when you use this material, when you apply stress, or let me just use different color. So, when you apply stress, this gives rise to polarization, and when you apply opposite stress, it reverses the direction of polarization. So, this is what you require to do with a ferroelectric material, a piezoelectric material, that you need to pole it before you use it as a piezoelectric. And this poling process is nothing but application of electric field to a virgin material and then bringing it back to 0 to create a domain structure which gives rise to a non-zero polarization. Okay. And lastly, and now I will give you some values of piezoelectric coefficients for variety of materials. So, because the magnitude of piezoelectric coefficient represents the extent of the effect. So, for example, for quartz you can have piezoelectric coefficient. So, D basically picometer per volt, and this is 2.3. If you look at the previous slides, so here basically I am looking at an indirect effect. So, picometer per volt. So, essentially if you have this converse piezoelectric coefficient, which is nothing but strain divided by the field, and this becomes volt per centimeter per volt. Or so 2.3 picometer per volt, barium titanate has a value of 100 to 150. So, reasonably large displacement. PZT, which is lead zirconium titanium oxide, this has 250 to 365 of the compositions which are close to morphotropic phase boundary, and then lead niobate, this has about 80 to 90. So, these are the effective. So, you can see that when you apply a volt, you essentially get a displacement of the order of hundreds of picometers. Now, what this means, 1 picometer is essentially 10 to the minus 12 meter, and this is essentially 10 to the minus 6 microns. Okay. So, when you apply just 1 volt, you have a displacement of the order of, let us say, 100 picometer. So, 1 volt gives you 100 picometer. So, when you apply 1000 volt, which is 1 kilovolt, you get 100 multiplied by 1000 picometer, and this is of the order of 10 to the power 5 picometer, which is 10 to the power minus 1 micron, and this is 0.1 micron. 0.1 micron is not a small displacement, it is a very large displacement, because when we talk about the when we talk about the material, the unit cells have the unit cell parameters are of the order of angstrom. So, if you look at the total displacement that the material has caused in terms of its dimension, it's very large, and given that, if you talk of now this may not be appreciable for a very big material, but when you talk about thick and thin film, this 0.1 micron is a very large displacement, and this is what makes them very useful in the form of actuators, transducers, etc., where this displacement is massive. So, now just like you have a ferroelectric material which can be poled, if you oppositely cycle a piezoelectric material or apply very high temperature, then application of this high temperature and large mechanical stress can also lead to disappearance of polarization. So, for instance, for a ferroelectric material, you know that as you increase the temperature, the polarization drops to 0. So, just like in ferroelectric material, in the piezoelectric material, when you apply large temperatures or when you apply large stresses, they can result in the depolarization. So, for this I will show you a video, and this video is taken from the Do It Pomps website. So, this is taken from this reference, which is doitpomps.ac.uk. So, you can go to this website. So, we acknowledge their support in putting up this on website. So, this thermal depoling, for instance. So, now you know the polarization, as it comes back to the Curie temperature, the polarization completely disappears, which means the dipole moments unalign. So, if you restart this, if I restart this thermal poling, so as the temperature is increasing, now you see how the polarizations moved. They were earlier in the reverse direction, and they have now moved into the direction, so that net polarization of the material becomes equal to 0. This is what is called as thermal depoling. So, it is opposite to poling. Poling is done to create a polarization. Depoling is essentially a process which leads to disappearance of polarization. Now, not only effect of applied field leads to depoling, but also effect of large electric field also leads to depoling. So, when you apply an alternating electric field to a piezoelectric material, and it generates a ultrasound because it undergoes deformation. So, as a result it creates ultrasound waves. Now the reverse, when you apply the reverse field, it depolarizes the piezoelectric, and this gives a strong enough field. So, if you restart this exercise, so if you look at it here, and you look on the right side. So, the net polarization of the material has, so this is, so as you change the polarity, look at the polarity, positive to negative, positive to negative. So, as you do this kind of depoling, you have the net result in the net decrease in the polarization of the material, simply because the reverse field which is created, that tends to depolarize the dielectric. So, this is because of converse piezoelectric effect. So, when you have direct piezoelectric effect, you apply stress, and this stress gives rise to polarization, but or electric field, but whatever is created as a result of application, that also leads to converse piezoelectric effect. So, both of these tend to fight with each other, resulting in the decrease in the polarization. And finally, you can also do mechanical depoling. This mechanical depoling is essentially basically when you apply a small stress to a piezoelectric material, this leads to development of a charge, as you already know from the direct piezoelectric effect. But the stress, normally we are talking about stress levels which are small, but when the stress levels becomes very high, these atomic positions can completely change. So, they do not remain in those positions at all. So, as a result, the dipole moment completely unalign, and hence the polarization disappears. So, if you restart it again, so just watch this here. So, when the stress magnitude has become very high, then the dipole moments do not remain as if they were just moving as if they were doing in the case of small stresses. So, essentially what you have is let us say you have this is a displacement of from the central position of central atom. So, when you apply small stress, this keeps flipping back, but when you apply very large stress in the opposite direction, this completely comes back here. So, as a result it flips over. So, the net polarization decreases. So, this is what was demonstrated in the previous this animation. So, if you just look at it again, when the stress is small, it just flips up and down below the equilibrium position. However, when the stress becomes large, then the atoms completely flip over from the previous position to a new position. As a result, unalignment occurs. So, basically what you have is depoling or disappearance of polarization by thermal means, by electric means, and by mechanical means. And basically the effect of all these three is to create conditions which lead to either conditions so that you have complete reversal of polarization in some region of crystal, so that you have zero polarization, or you have flipping of atom from its position to another position, which leads to again flipping of polarization in some regions of the crystal, giving zero polarization, or thermal means such that it just loses its polarization completely due to phase transition. So, so what you have here is depolarization of material. Now, in the next class what we will talk about is what are the kind of common piezoelectric materials, and how do we make piezoelectric measurements, and then what are the most common piezoelectric applications. So, we will stop here today, and these topics we will take up in the next class.